Okay, so quick review of the whole day. We got a clock with 12 o'clock here and so forth. And if it's 2 o'clock now, what will the clock read 37 hours later? And ultimately, 37 hours consists of 3 12-hour segments and another hour, right? So you can pretty quickly say it's going to read 3. So I think everybody understands that. If it's 7 o'clock now, after how many hours will it read 4 o'clock? Well, 7 o'clock to 4 o'clock, you can think about it. The 7 is here and 4 is here, and they differ by, 9 hours, right? So 4 o'clock comes 9 hours later, but it also comes 21 hours later, because every 12 hours it comes back to 4 o'clock, right? So we talked about that yesterday, and we figured that what you get is an expression like 9 plus 12n, if n is the number of complete cycles around the clock. Okay, so if n equals 1, you get 21. If n equals 2, well, you add another 12, right? If n equals 2, you get 24 here, and add 9, you get 33. So after 33 hours, it'll also read 4 o'clock, etc., etc. Okay? And I think people understood that when we talked about it. Okay. Now, we're trying to do an algorithm for this first problem, for figuring out what the clock will read 37 hours later, or whatever number of hours later. So we're going to do it in terms of symbols. We're going to let 37 be x. We're going to let t be your 2 or 2 o'clock. So it says as long as x is greater than or equal to 12, we replace x by x minus 12. Okay, now what does that do? Well, if t is 37, you're going to subtract 12 from 37, you're going to get 25, right? Now, x is now 25. It's still greater than or equal to 12, so we do it again. We subtract 12 and we get 13. We're not ready to end the as long as thing here. X is still greater than or equal to 12, so we subtract 12 again, we get 1. Okay? And then that's the end of it, because this condition is no longer satisfied. So we drop down to here and we add x to t. X is 1, t is 3, t is 2. We add them, we get 3, and that's it. It says now if x is greater than 12, then we do this again, because it's possible this would output a final number when we add t that's greater than 12, because x could be any number up to and including 12, right? Okay, so we do this. Now, there's some fits and starts in this, because I was thinking about how to structure it and a lot of other things, and I did a lot of dumb things, but when we finally got it in final form, that's what we had, right? And that's a procedure. I was pretending to do dumb things to illustrate the fact that when you're writing algorithms, you tend to do dumb things and you got to check things out. You've always got to check your algorithm out. I wasn't really pretending, I was really doing those dumb things. Okay? You will do dumb things too, hopefully not as many as I did here when you're trying to design an algorithm. You got to check it out. So over here we now just trace an algorithm. Okay, now here's another algorithm, and this algorithm doesn't work. Okay, and I ask you for homework to figure out why it doesn't work. Okay, so we just traced the values of z. Okay, x is, same problem, x is 37. Okay, so z is going to be 37. Now, as long as z is greater than or equal to 12, we do all this. Okay, so we divide x by 12, and that becomes z. Okay, that would be, in this case, 3 and a 12th. That has a fractional part. How do you get just the fractional part? Because the fractional part is the only part that really matters when you're going around this clock. It doesn't matter how many 12s you've done. What it matters is how much you've got left over, your remainder. So we're really trying to get the remainder when we divide z by 12, okay? And to do that, we subtract the greatest integer. Now, I think I made a note in your homework. I used brackets for the greatest integer, which is actually a standard mathematical notation as well as the floor thing, okay? And I couldn't get the floor symbols. I mean, I know what the HTML for the floor symbols is. It's an ampersand, L floor, semicolon, for left floor, the one on the left, or an R floor on the right. But it will not represent reliably on browsers. At least it wouldn't represent reliably in my HTML editor. So I didn't trust it, so I had to use the brackets, okay? So there we have that. We get 1/12, then we multiply that by 12, and bingo, we've got the remainder when we've divided 37 by 12, okay? And we've done it with simple mathematical steps, simple calculations, okay? We can't just write an algorithm that says figure out the remainder unless we've already got an algorithm to figure out the remainder, okay? So, you know, we could, if we had an algorithm to figure out the remainder and the program or the algorithm could access that other algorithm, we could replace all this by figure out the remainder. Well, then what do? Well, then we add the remainder to t, because z is now the remainder, right? When you multiply z by 12, there's the remainder. Okay, so we add that to t, which is our 2 o'clock, and we get 3, right? And then we keep repeating that. Problem comes, though, this seems to work. It gave us the same thing the other algorithm did. However, if we do it for t equals 8 and x equals 79, it gets screwed up, because when we do that, the z that we get here is, well, okay, when we add z to t, okay, I was looking at the wrong stuff. When we add z to t, we get something, even though z is less than or equal less than 12, when we add t, it comes out greater than 12, and we've got to go back here and repeat the thing. And when we repeat the thing, then we add z to t again, which means that this t, this 2 o'clock, or this 8 o'clock in this case, got added again. And that screwed things up and gave us the wrong result. And I didn't see that was going to happen, because when I wrote this down, I was a little careless. I wasn't testing as I went. You got to test. You got to make sure things work for any possible number. Now, mathematically, you prove algorithms, okay? In the art of computer programming, Knuth, now actually on his website, Knuth put a little note. Be careful about this algorithm. I've proved it, but I haven't actually tried it. Okay? You got to try it, and you got to try to beat it. You got to try to come up with numbers that screw it up. If you can't, that's good. And if you can mathematically prove that it works, then you take it to the computer and you run it a million times and see if it ever screws up. Okay? Okay. So anyhow, that's what you do. Now we're not going to learn computer programming, but you know, writing algorithms. A little introduction to algorithms. I think is valuable to you. Anyhow, that all happens, and hopefully you figured out how to rewrite that. I'll see when I look at your homework. And then we spent the afternoon doing circular models, and I did a quick review of this one yesterday. So I'm not going to repeat that, because at the end, you know, in about 10 minutes or so, I just reviewed all this. I did it all succinctly, so you have a short video reference if you need it. Okay? So what you got is a short reference to most of the stuff we did yesterday morning. Then you already have one for yesterday afternoon. And that came out to 9 minutes and 43 seconds counting.